Good morning, afternoon, or evening, wherever and whenever you are. My name is Benjamin, and this is part 14 to our Pixel Platformer series in Godot. In this video, we're going to be covering Delta. In the last video, I touched on it briefly, and I've kind of been having a lot of fun with all these different features that we've been adding into the game. And because of that, I haven't gotten around to Delta, but we need to discuss it. It's been put off for too long. It's time to talk about Delta time. Now, Delta time is a scary subject for a lot of people. But before we go into it, I do want to say that this series is made possible by the people who support me through my 1-Bit Godot course. If you're interested in that, there's a link in the description and in the pinned comment. I'm also going to be launching a YouTube membership program, which will be a way for people to support me and support this free YouTube content that I'm making if they don't really want to buy the course. If that's not a way that they want to support my channel, but they do want to support it with more than just videos or sharing the videos, then that will give an additional option to people. So that's not live yet, but I wanted to announce that that is coming soon, so keep an eye out for that. Okay, so what is Delta time? Well, games have kind of a loop that they run every single frame. That's what we call it, right? The frame rate. And that loop takes a certain amount of time in the real world, depending on how fast your computer's processor is and your video card. Basically, how fast your computer can handle the calculations in that loop. Okay? So what delta is delta is the amount of time that the last loop took. And so we use delta time as a way to try and project and guess how long the next frame is going to take in real life. So let's talk about the problem that delta time solves. Okay, so I've got a graph here that I've made in paint.net. On the y-axis, we have frames. You can see we go from 60 frames to 120 frames. And on the x-axis, we have our x position. So we're clearly moving our character along the x-axis by some amount to get them to this destination. So over time, their movement looks like this, right? This angle is their movement over 120 frames to reach some x position. And we could say this x position is 120, and then that would be a rate of 1 pixel per frame. So this is essentially our speed. However, this is frame dependent, okay? Which means that how long these frames take to process in real life could affect how quickly our character appears to move on the screen. Even though we're moving 1 pixel per frame or 1 x position per frame, it might take a different amount of time to get to that destination. Real life time. Let's see what that looks like. So we can actually grab this right here. Grab just this bit right here. I'll copy it. Oops, need to be on this layer. Copy it. And I'll come down here. Now, this graph, let's pretend that this is a scenario where our computer is running the game at 60 frames per second. And here we go, I'm lining up the graphs. And you can see that at 1 second, we've processed 60 frames per second. That makes sense. At 2 seconds, we've processed 120 frames. That makes a lot of sense. And our movement along the x position looks like this, right? Just like it looked before. Now, however, let's say that our game is processing at, instead of 60 frames per second, we're processing at 120 frames per second. So what would that look like? At 120 frames per second, it's going to look like this. Kind of jumped around there. You can see At 1 second, we've processed 120 frames, right? Now look at our movement across time, our seconds, right? If we overlay this movement, we've reached our destination in 1 second, where over here, we reached our destination in 2 seconds, okay? And this is the problem. This is what happens when you have your character's movement tied to the frame rate, or frame dependent. It becomes frame dependent. If we anticipate how long each frame is going to take, and then we multiply our movement or our change in position over time by that amount, that delta amount, then it makes our movement time dependent, real world time dependent, instead of frame dependent. Okay, and that is the problem that delta time attempts to solve. And if we come into our game, we can actually see this in action. Currently, if we come into our project settings and you search physics, in physics common, you can see our physics frame rate is 60 frames per second. Now Godot, it locks the physics frame rate to 60 frames per second. But depending on your game and and the player's monitors, you may want to allow the player to change this frame rate here so that it's not locked at 60 anymore. You may give them the option to try and match their monitor's refresh rate or something. So let's say we change our physics frame rate to, well, let's leave it at 60 for now, and we'll run our game. And you can see if we move our character, move pretty snappy, can move pretty quickly around in the level. Got a lot of gravity though. Something's wrong there. Okay, not sure what that was, if maybe the frame rate didn't update yet, or maybe my button wasn't working, it was releasing the up key. But yeah, we can move around in the world, and you can see if we double jump, we can jump about as high as that block over there, and it's pretty snappy. Now if we come into our project settings and set our frame rate to 15 frames per second, and you don't have to do this, I'm just using this as an example, it takes our character much longer to slow down. We're much more slidey, and we can double jump much higher. And so you can see that as we alter the frame rate, we're getting different outcomes. And this is because, for example, our gravity is being applied every single frame. And because we've altered the frame rate, now our gravity is affecting us less, because in the real time, it has less time to apply gravity. That wasn't the best explanation, but we'll get into this. You can see that it's not working. So we'll get into a better explanation right now. Okay, so when we're applying delta, it's important to know that first things, Godot automatically applies delta to your physics process or to your velocity, when you call move and slide. So Godot is automatically applying delta to this velocity. So we don't have to do this right here. Okay? However, when should you apply delta? Right? That's a very good question. A lot of people are not sure when they need to apply delta. Well, you need to apply delta to anything that is going to change over time. And over time, I mean over multiple frames. So that value is going to change over multiple frames. So what is velocity? Velocity is where is our velocity? Velocity is our change in position over time. Okay? And if that value is a constant, then you don't need to apply delta to it, because it doesn't change over time. But if that value, so for an example of that would be our double jump or our jump. You don't actually need to apply delta to our jump force here, because we're setting our velocity right here to a constant. This value is not going to, this y is not going to be changing over time in this case. It's just going to be set to a specific amount. So we don't need to apply it there. However, our gravity, you can see velocity.y plus equals move data.gravity. It is going to be changing over time. So this, our velocity.y is going to be added to every single frame, thus changing it over time and creating that graph that we saw at the start. So because our velocity is our change in position, you normally need to multiply your velocity by delta because it's changing your position over time. However, since move and slide already does that for us, we don't need to do our velocity. We don't need to multiply our velocity by delta. But our gravity is actually our change in velocity over time. So we're 2 levels deep. Velocity is our change in position over time, and our gravity is our change in velocity over time. Okay, so we do need to multiply our gravity by delta. In order to do this, we're going to pass delta into the different states that we have. So here we have our move state, and we pass in an input. We're also going to pass in delta from our physics process. So here we'll pass in delta. This is important. We'll do the same with our climb state. Delta. We'll come down to the climb state. And delta. Okay. Now we need to do it in our apply gravity. We'll pass in delta, delta. And then up here, when we're actually applying gravity, we have access to delta now, so we can pass in delta. Okay. So we pass it into the move state, which passes it into the apply gravity function, which then down here we can now use it, and we can say times delta. So we need to multiply our gravity value by delta because we're actually changing our velocity by that amount every single frame. It's the change in velocity over time. Okay. We also need to do this with friction. Delta times delta right here. Now we're getting an error because we're not passing it into our friction, so we need to come up here and pass it in delta. We also need to do it with our acceleration because both friction and acceleration represent a change in velocity over time, over multiple frames. So for our acceleration, we'll pass in delta. We already did friction, so we'll just do acceleration. Now we scroll down all the way to our acceleration function. Make sure we add delta as an argument to pass in, and then we'll multiply by our acceleration. So multiply by delta. Okay, now we're multiplying our character's movement by delta, and I think we got every spot. Oh no, we didn't get every spot yet. We have to do our climb state as well. And actually, we don't have to do our climb state. I forgot. And the reason is because our climb state, see our velocity, this isn't plus equals, it's just equals. So this is a constant. It's a constant, so we don't need to actually multiply. This isn't a change in velocity over time, right? This is just, we're setting our velocity. It's going to be the same every single frame that we set it. So it doesn't represent a change in velocity over time, so we don't need to multiply by delta here. Because move and slide will handle multiplying our velocity itself by delta. So we actually don't need to pass delta into the climb state. There we go. Now we can move, but we're going to have an issue, which is that, whoa, we move way slow now. Our gravity is way weird now. Why is that? Our project settings is set to 60 frames per second. But our character movement was set to values that didn't use delta. And now we're using delta. Now the physics process is 60 frames per second, which means that the values we're using for our character's movement are now 1/60th of the size that they were before, because now we're multiplying them by we're dividing them by 60, right? Yeah. So they're much smaller, or we're multiplying them by 1/60th. I think that's the same thing. If we come into our fast player movement, which is the one that we're using, we can identify values. Oh, there's one other value that we need to actually multiply by delta, which is our fast fall gravity. So this is apply gravity, and then we have fast fall gravity. So you can see this is plus equals as well. So we also need to pass in delta and multiply this by delta. And then it's going to error because we need to come into our move state and pass delta into this value, into this function. Okay. So let's go through these. So our jump force, our jump release force, those can be the same. Our max speed, that can also be the same because our move and slide is already multiplying that value by delta. So we're not doing it. Our acceleration, on the other hand, is our acceleration needs to be adjusted to account for the fact that we're multiplying it by delta now. And all we have to do is multiply this by 60. And you can do this right in the editor. So times 60, enter. It's 900. Friction is the same, times 60. Gravity times, that's going to be 300, but yeah. Additional fall gravity times 60. And then we can leave the climb speed the same because like our max speed up here, it's already being multiplied by delta. It was previously already doing that. Okay, now our character should move exactly how they moved previously. You can see we can jump about to the height of the blocks. Should be exactly the same movement that we had before. Okay? However, if we come into our project settings and set this to 15 now, it should account for this new setting. And you can see we can jump about as high as the blocks and the movement feels about the same. It's obviously way choppier because we're 15 frames per second now, but everything feels pretty much like it did before, other than being choppy. And if we were to set this to 120 frames per second, it would still work just like it did before. It'd be very smooth. Holy cow. I don't even think my monitor can show me the difference between 60 and 100. This might be just placebo on my end. I might not even be able to tell. It just feels nicer. So yeah, now we're properly accounting for delta in our movement. And we want to make sure that we're accounting for all of the different places that we've moved something. I'm pretty sure in our walking enemy, we were already... So our walking enemy uses move and slide, which automatically multiplies the velocity by delta. And since we have no acceleration, it's just a constant speed, we don't need to worry about multiplying that acceleration by delta. This is just a constant. If we come into our stomp enemy uses position.y, move towards, and we're already multiplying by delta here. Since we're not using move and slide in the stomp enemy, we need to make sure and multiply by delta. And we're already doing that, so we're good. And the spike enemy uses the animation player. Wait, where is it? Spike. Was it the spike enemy? Moving spike enemy. What is the spike enemy? Oh, that's spikes, not spike enemy. The moving spike enemy uses the animation player, so it should already have that problem solved. Now actually somebody, I think I already fixed this issue. What's this value? Yeah, 1.0. Move along path bounce. 0.99. So somebody mentioned, actually, while I'm thinking about it, that there is a solution to use, instead of using 0.99 here, we could leave this value at 1. This is I got distracted. So this is, remember the problem where sometimes our enemy, when it was moving along the bouncing path, it would like jitter at the top? There is a different solution for fixing that. Although I think maybe since I don't actually understand the solution. This one. You just uncheck loop right here, I think is what they said to do. Hopefully this is right. So we can come back into our move along path bounce and set this value to 1. And then if we come into the path follow, you uncheck loop. Is that what they said to do? I don't remember what they said to do. We might have just broke stuff. Okay. So that fixes that one, it seems. Does this one still work? And yes, that one still seems to work. It's interesting how that works. But yeah, that was their solution, which is a better solution. You can leave your move along path bounce value at 1, which is the value we would expect, and then you just turn off looping on your path follow 2D. So that solves that problem. Okay, so we have updated character movement to use delta. Let's go into our default movement data that we created and make sure and update it as well. So our acceleration is going to be 600. Our friction is going to be 600. Our gravity is going to be 300. Our additional fall gravity is going to be 120. And our climb speed and double jump, those stay the same. So we can come back into our player. We can drag our default movement, and this should work as well regardless of the frame rate. So yeah, this feels definitely slower and floatier. Maybe I'm just used to it, but I like the fast player movement more that we had for our character. And this all looks like it's working great. So that is delta, right? It can be a tricky subject because it can be hard to know where you need to multiply by delta. And it can be hard to understand what it actually is. But delta is just how long the previous frames took to process. And it's our attempt to guess how long this new frame is going to be. And then we multiply any change in some value over time by delta to make that change time dependent instead of frame dependent. So if it's our position, then we multiply our velocity by delta, which is our position's change over time, our positional change over time. We multiply our velocity by delta to make that change in position time dependent, real world time dependent, instead of frame dependent. That's the explanation of delta. Hopefully it was helpful to you. It is a complicated subject. If you have any questions for me, if you're not sure exactly what this was about, how it all works, feel free to ask in the comments below. I'll try my best to help answer. I hope this video was helpful. I hope this graph was helpful as a way to understand the problem, and that you understand the solution at least somewhat based on this video. And I will do my best to help answer if you have any additional questions on top of that. Thank you all so much for watching, and I will talk to you all later.